Hello everyone. So in this video, I'm not going to repeat the second lab session of R programming. So what I want to do is to briefly go through all the expressions and codes and try to explain some mistakes or questions you might have when you're running this code. So if you don't fully understand the code in the second lab, so you may find something helpful in this video. Okay, so let's get started from the first line of the code. So library, it is a command to help you to loading the package. If you already installed some packages, you can use the library, this command, to loading the libraries in your memories. After loading the package into your memory, you can use the packages. You can use the functions or data in that package. So otherwise, if you don't load the package into your memory, so basically you cannot use that. Even you may install that packages into your working directory. So MASS is a default library. So it's a library installed by default when you install R. So now we can just directly loading the library into your memory. So you don't have to install MASS library again. So if you click it here, so we run this execution. We run this expression. So now you have MASS library loaded. After you loading this new package of MASS, you may click on here. So in your environment, so you can click on this small arrow, you can see the package MASS. So that means that you load this package into your R memories. So now if you click on this, you can see this is something you can use, some functions you can use, and this is all the function names you can use in this package. Okay, so in this lab, we still need to install a new library called ISLR. So in the lab session, we briefly go through how to install the library. You need to go to this website. When you go to this website, you need to download a zip file and called Windows binaries, and this is the name of the zip file. Once you download that zip file, you can go to package, this panel, and click install, and there's two options because you already download the zip package, so you can choose zip. Once you choose zip, so you can browse and to try to find out where your package is located. So and then you can click install, so that could installing the new package into your R. After the installation, you can use the library to load the new package into your memory. So now we execute this. Now we're loading ISLR into our library. So if you click environment and click the arrow, now you can see this is ISLR. This is a new package we just installed and loaded. So in this package, we have some data sets. So we're going to use some of the data sets in this package for our lab session number 2. Okay, so once we load MASS package into our memory, so we're going to have some new data sets. So if you go into this package, if you click this arrow and this package MASS, if you click on this, so if you scroll down, so you will find this is all the data sets you could use. So among all the data sets, there's one called Boston. So this is a dataset name. So because we load MASS into our library, so we can use Boston datasets. So now if you in here type Boston, and now you have Boston popping up, that means okay, you have a Boston dataset in your memories. So now we hope to find out the data type for Boston dataset. And so we're going to use a class. So Boston, if you type BOS, now Boston will be popping up. So if you hit enter and then hit the enter again, so now we can see the data type of Boston dataset is a data frame. For a data frame, so we know data frame is to storing the tabular data. So basically you can understand a data frame looks like a table. So we'll have several different rows and for several different columns. For every columns, usually we have a name for different columns. So if we hope to know the names for different column, so we can use names. So this is a command to view all the names. If we execute this, so we can see, okay, so this is all the names. So, and also for this data sets, we can use this question mark to activate the help file. If we execute this, now we can view some help file for this data sets. So this is all the descriptions for different columns. Okay, so now we hope to use the two columns. One column is called MEDV, so this is the last column. So the meaning for that is the median value of owner-occupied home. So basically, this is the a column for the home values. So we hope to use another one called LStat. So this is a lower status of population. So that means a percentage of a lower income populations in a certain area. So we hope to use the two columns of data for our analysis. Now we're gonna assign the two columns to Y and X. So I hope you still remember this is assignment operators. So we're gonna assign this to Y. So what is this? So if we have the Boston, this is the data set name here, and following with a US dollar sign. US dollar sign is an operator to subsetting a certain column. If you, for example, if you're typing here Boston, and then you type a US dollar sign, now what popping up is the column name. So you will have all the column names popping up in here, so you can select. So what if you select the last one called MEDV? So if you click on this, now if you hit the enter, so R will display or print out all the data in that column. So that would be a lot of data. Okay, cool. We have more than 500 lines for this column. So this is the column for MEDV. So the same as that, we can also use Boston and with a US dollar sign, and then we can choose another column called L state. If you hit the enter, so that will print out all the data. So this is all the data for this column. So we can see, okay, so this is the way we're gonna subsetting different columns. Now we assign one column to Y, the other column to X. So now we got the data in here. So device.new, so this is to creating a new device for our plotting. If we run this, so that means we could create a new one. So we'll forget to run this. So we run this. So now we're using plot to see how it looks like for the two columns of data if you're plotting them together. If you execute this, now we got a plotting. So the horizontal axis is our X, X is the L state. So this is basically the percentage of a lower incoming populations. And so the horizontal, the vertical axis is Y, Y is MEDV. So this is basically the value of the house in this area. So we can see, so they have the two columns of data, they have a negative correlations. So basically we can observe a correlation from this directions. Okay, cool. So this is one way to plotting the two figures, the data in a figure. So we can try to create a new device, and so this is our new device, and this is empty. And then if we execute this, so now we got another figures in here. So in here, so Y is L states and X is MEDV. So MEDV. So this is slightly different from the previous one. Okay, so it really doesn't matter. So this is just how we're gonna plotting this. Okay, now after plotting this, we hope to do some linear regression analysis. So we hope to using our our X to predicting our Y. So we hope to find out a relationship between y and x. So usually the very simple functions or equations for the simple linear regression is y equals to ax plus b. So x is the L states. So we hope to use the percentage of the lower population, lower incoming population in a certain area. They use this value to predict the value of a house in this area, because the y is MEDV. MEDV, if you click on the hell, that's the mean value of the house. Okay, so and we are going to use LM, this function, for the simple linear regression. So LM is the function name. So we should give some of the arguments. So by default, we can just give one argument, that's the equation. So how to define the equation? So we're going to use in this format to define our equation. We write our response, so y, and then following by a small symbol called tilde. So, and this is a very special symbol. And then following by just our variables. So we only have one variable, which is x. So that means we hope to find out the relationship between y and x. So given y is the response, so x is our input, it's the variables, or we can call it a feature. So we can just give a function's equations format to the function LM, and then the function will do everything for us. So if we click on this, so basically it looks like, so we don't do anything, but basically, so the function did everything for us. So, because I hope you still remember, x is the value of L states. So x is a vector, and y is also another vectors in here. So basically, we're giving two columns of data to LM function, and that LM function estimates the A and B. So this is a linear regression model for us. So if we hope to take a look on the regression analysis results, so we can use a summary. So this is a command. So we can, if we execute this, so this is a result for our simple linear regression. So we got the coefficient for the interceptions, also coefficient for x. Okay, once we got the simple linear regression model in here, so we give it a name, fit underline LM. So don't confuse yourself, because we have LM on the right hand side and LM on the left hand side, but so they are completely different. So LM on right hand side, this is just a function in here. This is a function name. But on the left hand side, because in here we have assignment operators. So on the left hand side, so fit underline LM, this is just a name. So we're using this variable to store the estimated model. We can give whatever name we like. So for example, if in here, so I want to give it a name like my model 1. So this is just a name. So I want to do a simple linear regression y and with a tilde x. So I can do this. So and then after I got my model, so I can view my model by using summary command. So now I got this summary results. So this is the model estimation results. We got coefficient and different coefficients in here. So, and this is just a name. So this LM is not this LM. So because we have assignment operators in here. Okay, when we estimate the model, we can plot the model to with the original data. Let's see. So what is the relationship? How the model is a fit to the data. So we can use a line. So this is a command to add one more line to the plot. Because if you already got the plotting there, so you can use this function to plot one more line to the existing and plotting, because we already got this in here. So what we can do is we can try to run this, and you can see, so okay, so we got a red line in here. So, and we can also execute another one, so we can change to green and choose the very white lines. So this is all fine. And because And this is a simple linear regression model. When we got the model, maybe we hope to use the model to do some predictions. So, and how to do the prediction? So we're going to using the predict.lm. So this is the function we're going to use for predicting by using the simple linear regression models. So, and the way to use that is very simple. Is that we use this function. So we give the first argument. This is our estimated model. Second argument should be the data. But one thing we need to remember, once we're using this, we need to give the data frame typed number. So that means if we construct using C function, so that means X is a vector. So if we're using this, because we can auto printing X, so X is a 5, 10, and 15, so this is a vector. If we fit in a vector to the prediction model, basically it doesn't work. So that means we got some errors because we hope to, and so the function hope to receive a data frame rather than a vector. So we hope to we have to convert X to a data frame by using data frame. So this is explicitly a data type conversion. So we're going to convert X to a data frame. So that means if we execute this, cool. So X has been converted to data frame and assign that to new data. And so that means we're going to predicting by using this model with a new data of data frame. So, and then we got some results. So what is X? X is 5, 10, and 15. So now we got 3 results for X equal to 5, and X equal to 10, and X equal to 15. We can also try to calculate a confidence level. So usually we like to calculate a confidence level of 95%. So we can add intervals equals to confidence and give a level, default level. So that's usually 95%. So we can execute this. Now we got some results. So 1, 2, 3, and this is corresponding to X equal to 5 and 10 and 15. But for every X value, we can give out, this is our prediction value, and also we can give out, this is a lower bound and upper bound. So for every prediction result, you can have a lower bound and upper bound. Okay, so, and now we're going to moving down to multiple linear regression. So, and the first thing, what I want to do is to attach the Boston data set. So, the only reason I want to attach is once I finish attaching this, so I can directly using the column name to do some regression analysis. So that's a very convenient way to use different columns of data. So if I execute this, so basically that means I can have all the column names in our memories. We can directly using some column. For example, if I type in MED, so now MEDV popping up because MEDV is one of the column for Boston dataset. Okay. So now we want to do some multiple linear regression. So we still hope to predicting MEDV. So by using L state and age. So this is a 2 variable linear regression model. So and this is our response. So we hope our response equals to a coefficient times the first variable L state plus coefficient times the second variable age and the interception and plus the interception and plus epsilon, which is our error. So now we can still using LM. LM is a linear regression analysis function. So we can only give a one argument. This is the format of our model. So we write our response as the first one. So our response is MEDV, and then following by tilde. So this is a small symbol showing that. So before the symbol this is our response. After the symbol is our variable. So we got 2 variables, L state and age. Okay. So if we execute this, now we're finishing estimating our model. So if we execute this, we can see, so this is the details for estimating our model. So, and because we got our new model, we hope to do some predictions. So the new model is based on the regression of 2 variables in here. So that means for predicting any of the results, we need to provide 2 variables. So, and also we need to provide a data frame. It's not just the vectors. So we hope to construct some data frames in here. So this is how to construct a new data frame. So we use a data frame function. And so for the data frame, we have 2 columns. The first column is called L state. So we get 3 new values, 5 and 10 and 12 and 15. And another column called age. So for age column, we have 30, 40, and 53 different values. We hope to calculate the interval and confidence intervals. So if we try to do this, okay, so this is the result. So the first result corresponding to an L state equal to 5 and age equal to 30. So this is the lower bound, upper bound. The second result corresponding to an L state equal to 10 and age equal to 40. Okay, so, and we can also explicitly constructing our testing data by using data frames. So in a previous example, we don't construct our data set, so we just embedded our data frame constructing process into our functions. Now what we can do is we firstly constructing some testing data, and then so we're gonna passing the testing data to the prediction function and to do some prediction using our model. So this is how we're going to constructing some new data. So we're using data frame. This is a function. So for this data frame, we have 2 columns. One is called L state, and then the other one is called age. So we have the 2 columns in here. We're given the different values for different columns. We're constructing our testing data, and then we passed our testing data to the new to the prediction function. So we're going to do some prediction using our models in here. Okay, so what if we want to do some nonlinear regressions? So for nonlinear regression, usually the function of the regression model is a little bit difficult, a little bit complicated. So that's the reason we hope to explicitly defining our nonlinear regression model. So usually we use formula function. So if we could define using formula function, but the ways to define a function is more or less the same. So we write down our response firstly, and then followed by tilde. So after the tilde, so we're gonna write down the format of our regression function. So in this regression function, we hope to have 2 variables, but not just a linear variables. So the first one, we have the 1 variable, the second is the age variable, and the third item is the multiplication of the 2 variables. So this is a 1, 2, 3 part of the variables. So we construct this as a formula, and then we assign the construction result to this. So this is a variable. So this is assignment operator. So we construct something and we assign to a new variables. So the name is reg formula. So this is our formula. So once we construct our formula, so we can pass the formula to this as 1 argument to LM function, and then we're gonna pass some Boston data. So that means LM, so this function while using this formula and this data to do some nonlinear regression analysis. So if we execute this, so we got our function. If we auto printing this, so you can see, so this is our functions in here. We're auto printing our formulas, and then we just execute this. Okay, so if we show how our estimation looks like, so this is our estimation details. Okay, Now we're going to move down to logistic regression, so which is one of the most important models we discussed before. Okay, so for talking about the logistic regression, we would like to use another data set called S-Market. So S-Market is installed by the package ISLR. So if you go to the package panel, if you click on ISLR, and then you will see we got two data sets in here, S-Market and CarSits. So if you click on this, so now this is how this data set looks like. So we can take a look. So for this data set, S-Market data set, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 different columns. So first column is the year, and then we got the columns for leg 1, 2, 3, 4, 5. 5 columns for the legs. And then we got the column for volume and for today's price. And the last column, if you could take a look on the last column, is just up or down, up or down, up or down. So now, so if you are not very understanding on this, if you could check the help file and S-Market. If you give a question mark with a S-Market, if you hit the enter, so now you got the help files for this data set. So if you can check the descriptions for direction, so this is a factor with the levels down or up, indicating whether the market has a positive or negative return on a given day. So, and this is basically how the market is changing based on the data. So this actually means from yesterday to today, we have a market going up, and this keep going up as it going down. So we have the directions tags in here. So okay, now for our logistic regression model, so we hope to using most of the variables in here to predicting our directions in here. So we will see is it possible to do that. Okay, so to use the logistic regression, so we're gonna using the GLM. So GLM is a function to estimating logistic regression models. So if we hope to use a GLM function, we need to give some arguments for this function. So the first argument always be the model structure. So and to construct the way to constructing the model is the same as a simple linear regression model. So now we hope to forecasting our directions. So direction, apparently this is our response. So our response followed by a tilde, and then we're going to write down all of the variables we hope to use. So this is different lags and volumes. We hope to use the price lags and volumes to predicting whether the market is going up or going down. So this is our function. So and the data, apparently data should be equals to S-Market. So S-Market, we're going to using S-Market data, and family, so this is the distribution family, because we are doing the binomial, we are doing the logistic regression, so this is either 0 or 1. So for the direction is either down or up, so this is definitely binomial distribution. So we're going to using this function and to estimate a model. And so this is a function estimating model. So we're going to assign the result of the estimation to a variable called glm.fit1. So this is just a variable name. You can give any of the name you like. So this is I want to give this name. So this is just my preference. So whatever names you could have. So if we select the 2 lines and execute, okay, cool. So you finish the estimation. So if you click on this, you will see, so this is the estimation results for your model. So you have different variables like 1, 2, 3, 4, 5, and your columns. Okay, cool. So now you got your logistic regression models in here. So what we hope to do is to predict and using the model. So now we're using predict function. So we're using predict function and with some arguments. So the first argument is the estimated model. So this is our estimated model. So this is just a variable name and storing the estimated models from GLM function. So we give the estimated model as the first argument, and the second one is we give it a type. So what type of a prediction we like to do? So we like to having the response, because we are doing logistic regression. So the result for logistic regression should be a probability. So we discussed this in our lecture. So that should be a probability from 0 to 1. So that means that's going to be the response based on our model. So when we're using this function, we don't give any new data. So that means if we don't give any new data, so that means we are going to using the old data, which is the training data sets. So basically that means, so this result is from our training data sets. So that means we're using the training data set to estimate a model. Once we got the model, so we fit the training data set again into the model and to find out so what is our result. So if we execute this line, now we can get the results in here. So this is the result saving in this variables glm.probs. So this is the saving the probability of our results. So this should be a very long result. So we hope to take a look on the first 5 values of this result. If we execute this now, so this is the first 5 results from our predictions. So you can see this is approximately a 0.5 probabilities for every single value, so more or less than 0.5 probability. So this is the output for a logistic regression. So in the lecture we know logistic regression output the probabilities of 0 or 1. So this is all we get. So for the first point we get a probability of 0.5, slightly higher than 0.5. The second one is slightly lower than 0.5. So and if you still remember, because our response is when we're training the model, so our response is directions either up or down. So what we hope to do is we need to convert our probability to either up or down. So this is usually by defining a threshold. So in most of the cases, 0.5 probability is the threshold for determining 0 up or down. Usually we consider the probability higher than 0.5 is equivalent to 1, or lower than 0.5 is equivalent to 0. So on this case, because we are predicting the directions of up or down, so if the probability higher than 0.5, so we consider that this is up, and if lower than that, this is down. So to convert our result to be up or down sequence, so we're going to using if-else function. So if-else function is to convert our numerical result to be a logical result by using a certain function. So a certain condition. So the condition is the first argument of if-else function. So glm.probs. So this is a result for our logistic regression. So we got the results in here. So this is the prediction results. And so the first condition is if the probability is higher than 0.5. If the condition is satisfied, so we give the result of up. If not, so we give the result of down. So this is a very efficient way to do the if-else. So we convert everything together. So the first one is the condition. If we satisfy the condition, so we give it up, or otherwise we give it down. So by one expression, so we can convert our numerical result to be either up or down result. So now let's execute this, and maybe we can take a look on this. So if we take a look on maybe the first 5 and 1 to 5 values, so you can see, so this is our results, our logistic regression results, the first 5 values of logistic regression results. And when we convert it to up or down, so you can see the first value is slightly higher than 0.5, this is up. And the second is lower than 0.5, this is down. This is lower, this is down. So the fourth one is higher than 0.5, this is up. So, and the last one, the fifth one is higher than 0.5, this is also up. So by this sentence, if else, so we're going to convert our numerical result to probability results to up or down results. Okay, now we got up or down sequence in here. No, in here. Okay, cool. So now we hope to find out, so this is our prediction results. Are they equal to the same as the real results? So if we attach this and we're using a function called table, so now we can generating some confusion matrix. So this is very similar to confusion matrix. So the column, the first column is so the prediction results. So the prediction result of a down or up. So for the row, for the columns in here, it's the real directions. So so this table means for the real direction lockdown. So 145 down are predicted by down by the by our logistic regression model, and another 141 direction of up are predicted as down. So apparently this is a not good result. So that means approximately half of the real down are predicted by down, half of the real up are predicted by down. So this is almost a half-half accuracies. So if we take a look on up, so more or less the same. So for the direction, the real direction of up, 507 up are predicted by the model as up, and the other approximately 450 are predicted by down direction are predicted by the model as up. So this is almost a half-half and accuracies. So this is a really not a good accuracy. So this result shows if you're using this formula, so that means if you're using lag from 1 to 5 plus the volume to predict the directions, so we don't get a good results in here. So, but anyway, so we're not going to do like a modeling problems. We're trying to show how to use this R programming. Maybe you can choose different values of the different variables in here to predict and the directions. So we don't actually need to use all of the lags in here. So this is maybe too many. But anyway, so this is a one way we're going to using some data to fit the logistic regression model and try to do some predictions. So, and usually when we are trying to do some machine learning problems, so we only have a one big data set. So once we got one big data sets, we have to split the one big data sets into training data sets and testing data sets. So if we really want to do that, so this is how we're going to do by using R. So for example, so in this data set, so S market, so we're going to take a look at this data sets before. So this is how this data set looks like. So on the first column is the years. So we have the data from year 2001 to 2005. So that means we got 5 years from 2001, 2, 3, 4, 5. 5 years data. So, okay, now, so what if now we hope to use the data before 2005. So that means we use the first 4 years data to training the model. So this is the data in 2004, and so this is approximately the end of the data in 2004. Okay, so if we like to use the data before 2005, so to training the data, and we use the data in 2005 as the testing data to test the model. So how to do this? So we can see in the first column is our years. Maybe you can use some manipulations on the first column to find out so which data are before the 2005. Okay, so here it is. So this is how we're going to do this. So because we attach S market. So sorry, yeah, I've done the attaching. So after we attach this data set to our memory, so that means we can directly using the column name. So year is the first column's name. So year is the first column's name. Okay, so now we are using this condition is in here. If year smaller than 2005, So that by this, so the R will just calculating for every different elements in year. So I compare with different elements with 2005. If this is smaller than 2005, we'll give it a true. If higher or equal to 2005, we'll give it a false. So this is how we're going to generating a logical vector. So we give it a name of train. So train is actually generated a logical vector of index, indicating whether the year is before 2005 or at or later than 2005. So this is how we're going to generating a logical index. So once we got a logical index, we can using this as a subset. So that means we're going to using part of our data sets to training our model. So we don't use the all data in one data set. So we're using a subset of the data to training our model. So to do this, so we're gonna still using GLM function. GLM function is to estimate our logistic regression. So we used this before. So for GLM function, the first argument is to define our formula. So this is our formula. So the same as before. So we use direction as a response. So we use lag 1 to 5 plus the volume. This is the variables. And then we use the data. So S market, this is our data. Family is a still binomial distribution. And then we have one more argument called subset. So subset should be a logical vector. So that means we're using the subset of the data to estimate this model. Okay, and then we assign, using the assignment operator, assign the result to this. This is a glm.fit2. So this is a new model trained by part of the data sets in here. So if we execute this, so I forget to execute this. So, and then once I got the train, so I'm gonna execute this. Okay, so I just want to show you, once you execute this expression, so the train is actually a logical vector. So you may take a look on how train looks like. If we take a look on the first 10 elements, so you can see, so this is all true from here. So this is a logical vector. Okay, so once we got the model, so we can take a look on how the model looks like. So this is the estimation process for the model. And because we got a new model, we hope to use the new model to do some predictions using some new data. Because we use train. Train is the index, it's a logical vector. So we don't hope to use the same data for prediction. So we hope to use the other part of data. So we use part of the data, which is the data before the 2005. Now we hope to use the other part of data for the testing. So to do the prediction, we still use the prediction function. So the first argument of the function is the model. We estimated a model, so we fit the model into this function as the first argument. Second argument should be the data. But in here, this time, we don't use we don't use all the data, because the new data equals to is our data sets. But attention on here. So that means we're gonna take the reverse logic to the train. So train is a logical vector. So that means we don't need the training data sets. We need the other part of the data sets. So we take the opposite to our training data sets. So that means we got some testing data sets, and the type is also response. So if we do the predictions in here and then for the results, we're gonna using if else again to convert the logical results to up or down. So we execute this. So and then if we extract the real directions from the data sets, so now we can take a look on this. So this is our results. If we calculate the mean of the accuracies, apparently this is not good results. So probably the very bad accuracy is because of the model. So we're trying to use different format of the model. So this time we're going to try to use lag 1 and lag 2, only 2 variables to predict our directions. So we're going to using the same data set, so same subset, the same family binomial distribution, just a different models. So we're going to using the train this model. We give it a name glm.fit3. So once we got fit 3, so we do the same thing. So we do some prediction and convert the numerical result to up or down, and then we take a look on how it looks like, and we calculate the accuracies. So it looks like the accuracy is much higher than the previous one. So previous one's around at 48%. So now we got around 56%. So that's much higher than previous one. Okay. Now we're going to moving down to tree-based models. So for tree-based model, we need to install a new package. So this is a tree package. You should go to this website and download Windows binaries. So this is the file name for Windows binaries. Once you finish your installation, you can loading the package into your R program. So we're going to using library and tree. We execute this. Now we're loading tree-based model into our memory. Okay, so after we're loading a tree package into R, so we hope to use some tree-based models to modeling some real data sets. So now we're going to using a data set called car seats. So this data set is from ISLR package. So if you click on this package ISLR, if you click on this, you will see this is we got a data set called car seats. If you click on this, now we can take a look on what is a car seats. So this is basically a data set. We got several columns, and we got and 400 different rows. So we have a sales column and price column and income column, advertisement, so and so on and so forth. So basically what we hope to do is we're trying to using using some of the variables to predicting the sales. So this is what we're trying to do. Okay, so and because car seat is a data set, so we would like to know what data type it is. So we use class and car seat. So okay, so apparently this is also a data frame. So for the data frame, we can try to type in the we can call the function called names to show up all the column names. If you execute this, so we can see this is all the column names. Okay, before we try to predict some sales values, we're trying to see how the sales column distributed. So we create a new device, and then we draw the we're trying to draw the histogram. I'm sorry, I forgot to attach. So and I think this is a good example of the error. So because the sales is one column of the data set car seats. So if you want to just directly using the column names in here, apparently we got an errors in here because we did not attach the data sets to our memories. So what if we use a histogram in here and we type car seat? So this is our data set. So we're using a US dollar. And so what if we want to use the sales? Okay, and we got a 50. Now we can so plotting the histograms in here. So if we close this and we attach, so this data set. Okay, now I got this data set attached. So I can just directly using sales. So this is the column name. So now because I attached this, I don't need the data set name. So if we hit the enter, so now I got this histogram for the sales. Okay, so and what I hope to do is we got some numeric values for sales, and what we hope to do is to convert our sales number to a high sales or low sales and different labels. So this is something we try to do. So and by doing that, we can use we can using a classification model to try to modeling the problems. So, but first of all, we need to convert a numerical and sales number to the high or low. So basically, we're using if else. So we give it a condition. The condition is a sales smaller or equal to 8. So if the sales is smaller or equal to 8, so is it a high sales? Apparently it is not. So we'll give it a no. Or if it is not lower or equal to 8, so we'll give it a yes. That means yes, it is a high sales. So by this, we convert the sales, this is a numerical result to a vector of no or yes. So okay, so if we execute this, we can take a look on, so what is high? So we're going to take a look on the first of 5 elements. So this is a yes, 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 and no, no. Okay, so, and if we, for example, if we take a look on all the column names of this data sets, so we know this is all the columns. So now what we hope to do is we add one more column called high. So that means we hope to attach the new column into the data sets. So the way to do that is we're going to combine them together as a data frame, and we can assign the result to the data set again. So I execute this. So after this, if I take a look on all the column names, we find out that we got one more column, so called high in here. So okay, so now probably some of the students in the lab sessions make some mistakes because they by mistake execute this line for more than once. If we click it, run again, so that means we execute this combination for 2 times. Now maybe we got a problem. If we take a look on the column names again, you can see we got a high and high dot 1 because we're trying to, after we combine high and our data sets, so that means in our data set, we already got a column called high. So when we try to do this again, we combine another high to a data set which includes a high column. So that means we're going to have a 2 column sharing the same name. So this is not a good thing. So R automatically adding a dot 1 in here as the new column name. So if you are trying to modeling this, so maybe we got some problems because we're trying to predicting high. So, but if we are trying to predicting high using some of the data with high dot 1, so that means basically high dot 1, it is high. So they are the same things. We just by mistake try to combine the high data to the original data set for 2 times. So that means we're using the data to predicting himself. So that's going to be a problem. So if we by mistake have click on this, execute this expression for 2 times, so we're going to have to remove this. Otherwise, it's not possible to have a nice tree-based model. To remove this, I think it's pretty easy because this is our dataset's name. So I want to take just a part of the dataset, and as the result, so I want to take all the rows but just part of the columns. For the columns, that should be the first one to the number 12 column, because the last one, number 13, is high dot 1. This is something we don't need. So we're just subsetting this data set and assign the result to the data set again. So okay, execute this and we take a look on the names. Okay, now we remove the last one. So now we only got 1 high in here. So this is the data set we need. Okay, once we got that, so we can try to do some predictions in here. So okay, try to do some modelings in here. So we're trying to use the tree-based model. So the tree is a function. So the first argument is the model. So we're trying to construct the model using a very similar way as before. So high, that's our response. We hope to using some other variables to predict high. So now we have a tilde in here. So that means on the right hand side of the tilde, so we should have some variables. Now we got a dot in here. Dot means all the others. So all the others, but we should exclude sales because a high is generated by sales. So that means a dot and minus sales. That means so we need every other columns except sales. Okay, so that means we're going to using high, and take a look on this is all the columns. So we want to predicting high using all the other columns except sales. Okay, so and the data set is the car seats. So we're trying to run this. Okay, so we constructed the model. So let's take a look. So this the results for constructing the model. And if we're trying to plot the model, okay, we need to execute the 3 lines. The first line is we're going to create a new device. The second line is we'll plot the tree, and then we give some text for the tree. So now here it is. This is our tree-based model. So apparently we got it's not a very difficult tree. So we got a lot of different nodes in here, and every node we got conditions. So this is generated by our package. So it looks okay. Okay, so previously we just showed how to use the tree-based model. So this is a tree package to construct a tree-based model. Okay, now think about a real machine learning problem. So usually we got a data set. So we hope to constructing a model using the data set. So that means so we're gonna splitting the data set to the training data set and testing data set. So for the tree-based models, so this is the data set we're going to use. So, and we got 400 different data points. So if we're using this data sets to constructing a model and then do some testing, what we hope to do, maybe a better way is to we're randomly selecting a part of the data from this data sets. And then we're going to using the selected data to train our model. And then we're going to using the other part of data to testing our model. So, okay, so this is something we hope to do. So, first of all, we hope to randomly selecting part of the data. So, to do that, we're gonna first of all setting the seeds. So, setting this is only to make the results reproducible. Okay, you don't actually need to do this if you just want to do a random selection. Okay, now the second one is we try to select 250 data from 1 to basically the number of rows of this data sets. So that means 400. So because in here, so this data set we got 400 lines in here. So we're gonna selecting from 1 to 400. And so in this range, we select. We hope to select 250 points, and we assign that to a new variable called train. So train is going to be a new variable of index. So when we got that, so that means we got an index, a randomly selected index. So that index it could be used as a subset. Okay. Now we're going to using the tree function again to construct a tree-based model. So when we use the tree-based function, so the first argument is going to be the model. So constructing the model is basically using the same way as before. So high is our response. And we have a tilde in here, and that means on the right hand side of the tilde, so we got we should indicating the variables. So now we got a dot, so that means all the other variables. Now we got a negative sales, that means we need to exclude the sales columns in here. So that means we're going to using all the other columns and excluding sales column to predict high, so high or not. So the data is a car seat, and subset is train, which is generated in using random samples in here. Okay, so we're trying to execute, and so this is our train. So if I take a look on, so what is train? So if I take a look on the first 10, okay, you can see, so this is basically the random numbers from 1 to 400. Okay, cool. So, and basically we generated a random index, and then we train the model, and then we try to plot the model. Okay, so now we got slightly different models in here. Cool, that looks very interesting. So once we got a model, we're trying to predict. So we're still using a predict function, and we give it a model, we give it a data. So apparently we use a negative, and to indicating we don't need the train, we need the other part. So that means everything except the training lines. So the type is a class. We're trying to do some classification. So we click on here, so we finish our predictions. And then if we combine them together, so, and if we execute this, so basically we reach around 70%. So this is our result for accuracies. So it's not very good. So that's the reason maybe we need to use some random forest. So before that, let's take a look back on tree-based models. So basically, and tree-based means, and if we got a lot of data for every data points, we got a lot of different features. So every time we will want to split a tree, so we're gonna randomly selecting, well, not randomly. So we're gonna selecting one feature, try to minimize our and sum of the square error. So we're selecting one feature in all of the features, and we do the first separation, and then we got two regions, and in each of the region we do the feature selection again. So we try to do that again until some stopping criteria. So which usually is the number of the data in a certain region is less than the threshold. Okay, so that means for the separations, every time we need to randomly, we need to select one feature from all the features. And so for the random forest, we discussed that before, so we don't actually select the feature from all the features. So every time of the split, we hope to randomly selecting a certain numbers of features. So we're gonna do the separation based on those features. And every time when we do the one split, so we're gonna do this random selection again. Okay, so this is the theories for random forest. So now we need to go to this website and download the package called random forest. So once we download the package, we can use the package and install. We're gonna finish the installation. After we've installed the random forest package, we can loading them into our R. So you got a warning. Well, that's okay because they want to show you some new features. Okay. Okay, now, so we hope to use a random forest to do the same modeling and predictions as before. So we use the random forest function. So this is from our new package. So we use the same data sets in here. So, and we also hope to use all the other variables excluding sales and to predict high or not, high sales or not high sales. So we're also using the same subset. So we're gonna try to execute this. Now we got some models in here. So we're using a model to do the predictions. So the syntax is almost the same. We're using prediction function, so we give it a model. Now this time it's a random forest model, and we're given a data. So this is the testing data. So we use the negative sign to indicating we don't use the training data. And type is the class. So we click on this. So we do some predictions, and then if we click on this, now we will see. So this is our results. If we click on this, so we execute. So this is the accuracies. So as before, so if we compare the results and with the single tree-based model, so this is around 76%, so it's much higher than 70%. Okay, now I want to just move down to the last part of our lab session. So for this part, may be slightly difficult. So we're trying to find out for one parameter for random forest model. So we hope to find out the optimal value for that parameter. So the parameter is called mtry. So mtry is a parameter to control the number of features to be randomly selected for every split. So, because in random forest, so the theories for that is we need to creating a lot of different trees, and for every tree, so we're gonna do some split. But at every time we want to splitting a tree, so we hope to randomly selecting a number of features. but how many features we should randomly selecting? So that's going to be a problem. So by default, we're usually using the square root of our total number of features. So this is by default. So maybe the default is a good one, but maybe not an optimal one. So we hope to find out, and we hope to know so how the accuracy is going to be changed when we change the M choice in here, which is the features and random selected features every time at a split. Okay, so we hope to try. We hope to try 14 different values for mTry. The reason is that we hope to use the Boston datasets. If we take a look on Boston datasets, we got 14 features in here. So basically, we only got 14 features, so we hope to try from 1 to 14. So to do this, so first of all, we're creating a new variable. So this is just a variable called number, mTry number. So we give it just a constant number, 14. Okay, now we're creating the empty numeric vectors. So, and this is the way we're going to creating double. So double is the data type. So this is a numerical vector. So for 14 different elements. So if we execute this and execute the following 2 lines, so now we created 2 empty and numeric vector. So if we auto printing this, let's take a look. Okay, this is all 0. If we auto printing the other one called testing, so this is also all empty. Okay, fine. So that means now we have the 2 vectors to containing our future calculation results. Okay, now we hope to use a for loop in here. So in for loop, so we're going to go through all the numbers from 1 to try number, which is a 14. So we're going to try for every single elements from 1 to 14. So for every value of try, so we try to construct a model. So this is the way we're constructing the model. We're still using the random forest function, and so the first one is always be the function, always be the formula. So we're going to try to use all the other variables to predict MEDV. Okay, so because the MEDV followed by a tilde and followed by a dot. So that means we hope to use all the other variables to predict this. And dataset is the Boston, subset is the train. So we're gonna try to use a subset of the training dataset to train this. And then mTry. So mTry is a variable in 1 to mTry number. So every time mTry will change. So from 1 to 14. So we'll give it a fixed number of trees. So as the 400. So 400 is the number of trees we're going to generate it. So so this is the first line. We constructed the random forest model, and we assign the model to fit. So fit is the model's name. It's a variable containing the results. Okay, once we got this results, so that basically means we got some more than just a training set, more than just a training model. So we still got some MSEs, so that's basically training errors. So we hope to find out what is the training errors. So, and also after that, we hope to do some predictions using the fit. This is our model. So we also using the predict function to give it a model and also give some data. So the data is the Boston data set, and then we're going to using the index. So this is a not training index. That means this is a testing data set. So after that, we're going to try to calculate the MSE for the training data sets. So we're going to calculate that like this. So the MEDV, so that's the real data, and this is our prediction. So we calculate the difference, and we calculate out the square of the errors, and we calculate the mean. So we assign the results of the training MSE, training errors, to this empty vector. So every time when mTry having different values. So for the first time, m try is equal to 1, so that means we're gonna saving the results for the random forest model, and in the first data, in the first place in our empty vectors, the first place means m try equals to 1. So also we're gonna saving in the testing empty vector at the first place, we're gonna saving for m try equal to 1. When m try equals to 2, so we calculated the training error and testing error. We save the errors at the second place in the 2 vectors. And 2, so we're gonna keep doing that until the last one, number 14. And after that, we're gonna print. So what is m try? So every time we're gonna print m try. So every time when we have the different values of m try, we're gonna print it out. So we're gonna see how this loop is progressed. So if we select them all and try to execute, so we will see, so this is a printed results from m try equals to 1 until maybe 14. Okay, cool. So after we got that, we can see, so if we execute them together, so we will see, so this is some results in here. So we can see this is a quite interesting results. When we have the m try around this value, so apparently the testing results, we got the lowest testing error and also lowest training errors in here. So when m try is increased, maybe we got even higher errors in here. So probably at this area, for example, the 7, probably the best choice for m try. So this is how we're gonna compare different performance and based on the different m try values. Okay, so this is about the lab number 2. So in this lab, we discuss basically many different type of models, from the simple linear regression model to the logistic regression and tree-based and random forest. So probably this is a lot of different stuffs. So I guess maybe you should review these codes and expressions for many different times and try to understand for every single details in here how to use them. So in the next lab, so we're going to do some even further modeling problems, and also we will going to have an example of real machine learning problem solving. So for example, if we got some problems, if we got some data sets, so how we're gonna using machine learning to solve that using R programming. So we're gonna show, so what is the process when we got a data set and trying to solve some problems. That's basically in our lab number 3.